In the next block of code, we can instruct PyTorch not to compute gradients. We use the In this lecture, we are going to do an example of simple linear regression in code using PyTorch. In other words, we are going to learn how to find the line of best fit. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. To start, we're going to do a few imports. You'll see throughout the course that these imports are what we'll need pretty much every time. So we have torch and torch.nn, which is a module that contains a lot of useful stuff in PyTorch. Next, we have numpy and matplotlib. Numpy is for doing linear algebra and matplotlib is for doing plotting. Next, we're going to generate some data to apply our model to. Now you might ask, why aren't we using real data? Well, don't get too excited, that's what we're going to do next. Using synthetic data is actually very important in machine learning, but more on that later. So to generate this data, I'm going to set n equal to 20 data points. Remember that our convention is to use the capital letter N to represent the total number of samples and the capital letter D to represent the total number of features. As we move on to more complex datasets later in this course, there will be some additional letters. In our case, d equals 1, so we don't really need to specify anything. Next, we're going to generate some random points on the x-axis. They're going to be uniformly distributed between -5 and +5. There are, of course, several ways you could do this, so if you don't like the way I've done it, you can feel free to implement your own. And this applies to anything in this course. So what we've done here is generated 20 random data points using the random function, which outputs random numbers between 0 and 1. Next, we multiply those numbers by 10, so that they'll range between 0 and 10. Finally, we subtract 5, so the range becomes -5 to +5. Next, we're going to generate the data points on the y-axis. Because we're doing linear regression, we would like these y data points to be linearly correlated with the x data points. So to do that, I'm going to say y equals 0.5 times x minus 1 plus some Gaussian noise. Pay close attention to these numbers. This means that our true slope is 0.5 and our true y-intercept is -1. These are the values that our model is going to try and find. Now you might ask, why have I added Gaussian noise with mean 0 and variance 1, rather than some other kind of noise? In fact, when we have Gaussian noise, the mean squared error becomes the correct loss function to use, and thus, since we're using the mean squared error as our loss function, we would also like to use Gaussian noise centered at 0. You're not expected to understand this during this course, but when I mention these things, people inevitably end up asking me why this is the case. So if you are interested in learning the answer, I recommend you look at the in-depth series of courses where I've already covered all this material. Next, we're going to do a plot of the data. As you can see, it sort of roughly forms a line. It's a little bit hard to tell since the noise variance is quite high compared to the variance of the data itself, but I think it's pretty clear that the data is trending upward. So that's everything for our dataset. Next, we have the PyTorch stuff. First, we're going to define our model. As promised, it's just one line, nn.linear11. This means that we're creating a linear model with one input and one output. Next, we're going to begin the training process. As you know, this starts with defining a loss function object and an optimizer object. Luckily, you've seen this before, so there are no surprises. We're using the MSE loss and SGD optimizer with a learning rate of 0.1. Next, we're going to transform x and y into data types which are appropriate for PyTorch. So we start by reshaping x and y into n by 1 matrices. Next, we cast both x and y into float32s and convert them into torch tensors. In the next block, I printed out the type of the input's variable, so you can see that it is indeed a torch tensor. Next, we have our main training loop. To start, we set n epochs, the number of iterations of the loop, to 30. Now you might ask, why did I choose 30 and not some other number, like 10 or 5 or 1000? Well, the trick is, I've ran this script before and tried different values already. As a student, you don't really see all the work that goes into choosing hyperparameters, you only see the final result. So you might assume that you can just pick any number and everything will work out great. This is often surprising for beginners. In any case, I discuss a lot about hyperparameters elsewhere, so if you're interested in that, please ask me about it on the Q&A. Something else you didn't see in the code preparation lecture is that I have a list of losses that I'm going to plot after we are done. In each iteration of the loop, we are going to store the loss in this list, and at the end, we're going to plot the loss per iteration. This will let us understand whether or not we chose good hyperparameters, and whether or not the training process converged, and so forth. So it's quite useful. Oh, and just a hint for future examples. We are pretty much always going to plot this after training. So I don't want anyone asking me, what does this plot mean? Because it's going to be the exact same thing every time. So don't forget it. Alright, so next we have our training loop, which we've seen before. As I mentioned before, the first step is this weird step. We zero the gradients. And this is because, behind the scenes, PyTorch is actually accumulating the gradient each time you call backward. So this will zero the gradient to prevent them from accumulating and give us the correct answer. Next, we do a forward pass to get the model predictions. Since you've now seen how to make predictions and get the output as a NumPy array, you know this is similar to that, except we don't need to take the additional step of converting this into a NumPy array. This is all in PyTorch land, so we get out a PyTorch tensor that we can apply in the next step. The next step is to calculate the loss, using the criterion we defined earlier. Next, we save the loss to our list of losses. In this case, we do want to take the loss from PyTorch land into Python land, so we call the function item. Now you might ask, why do we call the function item and not the function numpy, like we do when we make predictions? And that's because the loss is a single Python number and not a numpy array. So when your tensor is a single number, and you want to bring that number back to Python land, then you should use the item function. Next, we calculate the gradients. PyTorch encapsulates this in a function called backward, to be called from the loss tensor. Finally, we call optimizer.step to do one step of gradient descent. As always, I like to print out useful information while the loop runs, so here you can see I'm printing the iteration number, along with the corresponding loss at each iteration of the loop. So if you look at these numbers, they give you some sense of how training is progressing. But the real value comes from plotting the loss per iteration, which is what we have next. This is the kind of curve we like to see in deep learning. A steady decrease downward, fast at the beginning, and slow at the end. This plot gives us more confidence that training has completed successfully. It's not a 100% guarantee, but this is at least one positive sign. Next, we're going to use our trained model to make predictions and plot the result. As you recall, our task for this model is to find a line of best fit. It would be quite silly if we didn't actually plot that line. The next step is therefore to pass our inputs into our model, which gives us the predictions in terms of a torch tensor. Since we would prefer to work with numpy arrays, we first detach the tensor and then call the numpy function. Now you might be wondering, what happens if I do not call detach? We'll look at that in a moment. The next step is to plot the data points using a scatter plot, and then to plot the predicted line using a line plot. As you can see from the result, our line is in fact the line of best fit. Next, we look at what will happen if you do not call the detach function. As you can see, we get an error. It says, can't call numpy on variable that requires grad. Use var.detach.numpy instead, which is exactly what we did. However, this error message gives us a hint for an alternative way to make predictions. We can see that it has something to do with gradients. In the next block of code, we can instruct PyTorch not to compute gradients. We use the context manager with torch.nograd. Inside the block, we make our prediction, but if you notice, there is no call to the detach function. As you can see, the output is printed correctly without any error. The last thing we would like to do in this script is to inspect the parameters of the model to check if they are close to the true values. As you recall, these are the slope and intercept of the line. In machine learning, we call this the weight and bias. In order to get these values, we call model.weight.data.numpy and model.bias.data.numpy. Intuitively, you can expect that model.weight and model.bias store the weight and bias as some special PyTorch tensor variable. However, we would like to bring these back to NumPy land, so in order to do that, we call data.numpy. You can imagine that the reason we treat these differently from the model's predictions is because they are model parameters rather than data inputs or outputs. If we look at the values, we can glean a few key pieces of information. First, the obvious thing we want to check: are they close to the true values? We get 0.46 and -1.2, so it appears that they are. One interesting thing about these is that W seems to be a two-dimensional array, whereas B seems to be a one-dimensional array. You might ask, why do we need a 2D array and a 1D array to store single numbers? In fact, we don't, but we need our model to be flexible enough to handle different scenarios. These scenarios are what you'll learn about in later lectures. The final thing I want to talk about in this lecture is, what is the point of using synthetic data instead of real data? This is going to come up once or twice in this course, so it's good to discuss this early and often. One of the most important questions we can ask is, does our model actually do what we think it does? As a beginner taking a course, your automatic reflex is to make a guess, or to think of the problem philosophically. But this is not a philosophy course. It is a computer science course. We don't discuss maybes in this course. It's binary, yes or no. It works or it doesn't. So synthetic data is very useful in that regard. I can create synthetic data such that if my model does what I say it does, then it will find the pattern in the synthetic data that I set it up to find. If it can, then my assertion is wrong. Doing things this way allows us to test the strengths and weaknesses of our models and to help us understand what they can and cannot do.